So far, we've been using solve as a black box. Now we're going to start to find out what's going on inside that box. Gaussian elimination. It's named after Gauss, but it actually was discovered at least 2,000 years ago. It's been written up in a Chinese text. In Europe, it was discovered by Isaac Newton and Michel Rolle in France. Gauss called the method common elimination. He came up with a way to use it to solve another problem that we'll get to later, and came up with a notation that was widely adopted. What's it good for? Well, can find a basis for the span of given vectors, which also will give us an algorithm for rank, and therefore an algorithm for testing linear independence. Can be used for solving a matrix equation, which we know is the same as expressing a vector as a linear combination of other vectors, which is the same as solving a system of linear equations. It can be used for finding a basis for the null space of a matrix, which is the same as finding a basis for the solution set of a homogeneous linear system, which we know is relevant to representing the solution set of an arbitrary linear system. The method is based on the idea of echelon form. Well, here's an example of a matrix in echelon form. Now notice that the first non-zero entry in row 0 is in column 1. The first non-zero entry in row 1 is in column 2. The first non-zero entry in row 2 is in column 4. And the first non-zero entry in row 4 is in column 5. A matrix is in echelon form if it satisfies the following condition. For every row, if that row's first non-zero entry is in position k, then in all the previous rows, the first non-zero is to the left. As a consequence, as you go through the rows, the non-zeros form a sort of staircase descending down. So, for example, here's the staircase for this one. Here's the staircase for this matrix. Notice that if a row is 0, then all subsequent rows also have to be 0. What good is it having a matrix in echelon form? One thing is that that the non-zero rows of the matrix form a basis for the row space of the matrix. For example, in this matrix, a basis for the row space is given by these first two rows. In particular, if every row is non-zero, as in these matrices, then the rows form a basis for the row space. We know that the rows generate the row space of the matrix. That's the definition of row space. So what we'd have to show is that the non-zero vectors are linearly independent. And to do that, we'll use the grow algorithm. So remember the grow algorithm. Let's try it out on this matrix. Adding the rows in reverse order. Initially, S is the empty set. The algorithm considers adding the last row. Now, since span of the empty set doesn't contain this row, the grow algorithm will go ahead and add it. Next, now S consists just of that row. Now, every vector in span of S has zeros in its first three entries, positions 0, 1, and 2. So span S doesn't contain this second row. So the algorithm goes ahead and adds that. Now S consists of these two vectors. Now, still, every vector in span of S has a 0 in positions 0 and 1. So span of S so far does not include this vector. So the grow algorithm goes ahead and adds that. Now S consists of these three vectors. Every vector in span of S has a 0 in position 0. So span of S doesn't include this vector, so the GROW algorithm goes ahead and adds that as well. We know that at every stage in the execution of the GROW algorithm, the set S is linearly independent. So we've shown that all the rows of this matrix are linearly independent.